Hi guys, in this video we are going to introduce you to the topic of infinite limit and limit at infinity. In daily definition, we know that limits refer to a point or a level that the object cannot go beyond or past. For example, money in my wallet, which is limited. But in calculus, limits refer to what value a function is approaching, as the independent variable approaches a specific value. Infinity, on the other hand, refers to the concept of something that is unlimited, endless, without bound, like my love for you. You might be familiar with the terms infinity with time, numbers, or even the universe. Similarly, on concept of limit in calculus, infinity can mean that, first, the limit does not exist, increasing or decreasing without bound, or two, limit does exist when the amplitude decreases which approaches a value of line y or going toward the line y, but does not touch it.
Infinite limits is a limit in which f(x) increases or decreases without bound as x approaches c. From the graph as well as the table, you can see that f(x) decreases without bound as x approaches 2 from the left and increases without bound as approaches from the right. This unbounded condition can be described as an infinite limit. Hence, we can denote the behavior of f(x) as x approaches 2 from the left and from the right as negative and positive infinity. However, the equal sign in the statement does not mean that the limit exists. In fact, it tells us how the limit fails to exist by denoting the unbounded behavior of f(x) as x approaches c. Infinite limits can be applied to describe the behavior of graphs with vertical asymptote. Vertical asymptote is the line x equals c, where f(x) approaches infinity as x approaches c, from the right or from the left. We can determine infinite limits and the vertical asymptote of the graph by calculating the denominator of a function by finding any number that makes the denominator equals to 0, but not the numerator. For example, f(x) equal 1 over 2 bracket x minus 1 bracket can have the denominator as 0 when x equal to negative 1, but not the numerator. However, this direct method may not work with a function like this because we will end up with 0 over 0. We call this as an intermediate form, and this form cannot use to determine the limit behavior without further investigation. Therefore, sometimes we need to factorize or simplify it. Also, in some cases, if numerator is factorizable, we need to simplify them. And after simplifying them, if there is a common factor, factor them out to find the real vertical asymptotes. By applying all the information we learned, we should be able to find a vertical asymptote of the given function. However, it is almost impossible to determine the behavior of the graph without further investigation. Therefore, the method of determining infinite limits will come to have a role, so we can determine whether the graph is increasing or decreasing without the bound. For example, we answer that this given function has a vertical asymptote at x equal to 1 by applying a few steps. However, to find the behavior of a graph from both sides, we need to find the infinite limits of the function as x approaches 1 from the left and from the right. By doing this, you can analyze functions with value of x close to 1 on each side. In other words, finding one-sided limits. After a few steps of calculation, you will be able to conclude that the limit of this given function from the left side is infinity, and the limit of this given function from the right side is negative infinity.
So the next topic is 3.5 limits at infinity. So from this table, you can see that if the value of f of x are getting closer to a certain finite value, which in this case, f of x is approaching 3, as x approaches positive or negative infinity, then the line y equals 3 is the horizontal asymptote of the function. So what's the definition of horizontal asymptote? The line y equals L is a horizontal asymptote of the graph of f when the limit of f of x as x approaches negative infinity or positive infinity equals to L. From this picture, the amplitude of the graph is getting smaller, meaning that it is approaching a specific y value. Next, we're moving on to the calculations part of this topic. So there are 3 occasions, which the first one is when the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. The second one is if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. The third one is if the degree of the numerator is greater than the degree of denominator, then the limit of the rational function does not exist. So for the first occasion example, the degree of numerator, which is 1, is less than the degree of the denominator, which is x squared. So the limit of this function is 0. Another way you can do it is by dividing both the numerator and the denominator by x squared, and the result you'll get is 0. You notice that 5 over x squared here is substitute with 0 because any x to the nth being a positive power as the numerator, the value of it is very small, so we can disregard it. Moving to the second occasion, you can see that the degree of x squared is equal to the x squared, so the answer is the leading number of the coefficient, which is 2 over 3. You can also calculate it by dividing both the numerator and the denominator by x squared. And for the third occasion, the degree of the numerator, which is x cubed, is greater than the degree of the denominator, which is x squared. So we get D and E as the answer. The limit does not exist. Or you can choose to divide both the numerator and the denominator with x squared, and the answer you'll get again is does not exist. So moving on to functions with two horizontal asymptotes. So this particular function, you'll see roots, and your x will be going towards positive or negative infinity. So if it's a positive infinity, you do not need to add negative sign in front of the root. You can just solve it regularly by dividing the numerator and the denominator with x, like this example. But if it's a negative infinity, you do need to put the negative sign in front of the root, then solve it regularly. And here's the graph.
I know it is a bit confusing between the topic of infinite limit and limit at infinity. However, it will be a lot easier if you can spot the difference. First of all, infinite limit is a limit which f of x approaches infinity, while limit at infinity is when x value approaches infinity. Second, infinite limits are dealing with the vertical asymptote, while limits at infinity are dealing with the horizontal asymptote. Third is the method of calculating. Infinite limit uses one-sided limits, while limit at infinity will use the three rational functions. Thank you for your attention on our video. We hope this is helpful to you. Bye!